Welcome to the STEM Sessions podcast. I am Jarl Cody, your host and narrator. Since last fall, I've been attempting to compost. I thought I did enough research up front. I bought an open-air bin that was both functional and reasonably attractive since I planned to place it in a visible corner of my yard. I educated myself on the proper ingredients and amounts thereof. I even got my wife excited about the venture. Yet, results were very slow going. I could tell there was a bit of composting going on, but not much. Certainly not what I was expecting. I tweaked a parameter or two, but saw no real improvements. Truthfully, I was frustrated and all but gave up. I continued to add new material and turn the pile, but I just stopped paying attention. If it happened, it happened. If it didn't, oh well. Then, one morning while watering my garden, I decided to give the compost pile another turn, and something started filling the air above the pile. My first thought was it must be dust. The material had somehow become so dry, small particulates were blowing off the pile. But then I realized it was actually water vapor condensing in the cool air. So I reached down, and the material was hot. I had achieved thermophilic composting, and I was filled with giddiness. This is the STEM Sessions Podcast, Episode 9, Adventures in Composting. When organic matter dies or is no longer able to repair itself or regenerate, it begins to decompose, a process in which its complex materials and compounds are broken down into smaller and less complex matter. Whether you look at this through the lens of entropy or the nutrient cycle, decomposition reduces organic material into its basic blocks such as water, simple carbohydrates, proteins, minerals, and salts. All organic material eventually decomposes given enough time, but specific environmental factors dictate the speed at which the process occurs. These factors include the amount of oxygen and water present, the ratio of carbon to nitrogen in the organic material, the size of the material pieces, and the presence of decomposing organisms like bacteria, fungi, and worms. In composting, we seek to optimize these conditions to complete the process of decomposition as quickly as possible. More specifically, composting seeks to optimize the process of aerobic decomposition. In aerobic decomposition, the complex carbohydrates and protein molecules are fed upon by bacteria and other organisms. As part of this process, the bacteria consume oxygen. In fact, consuming oxygen is a vital part of the process, as these bacteria use the oxygen to metabolize their food into energy, like all animals do, and thus can only survive in an environment containing oxygen. The primary byproduct of this process is carbon dioxide. At the same time, composting seeks to minimize the amount of anaerobic decomposition. This metabolic process occurs in the absence of oxygen and results in byproducts of acids and odorous gases such as methane and sulfur compounds. A compost pile undergoing aerobic decomposition will smell like healthy, nutrient-rich soil because that's what it is. A compost pile undergoing anaerobic decomposition will smell like rotten eggs or a dairy farm. This is why ensuring a compost pile is properly and continuously aerated is critical. It needs oxygen. Efficient composting also requires the right mix of carbon and nitrogen, with most guides setting the ideal carbon to nitrogen ratio at around 30 parts carbon to 1 part nitrogen. Carbon takes longer to break down, so too much carbon in your compost pile will cause it to dry out and slow down the process. Nitrogen decomposes very quickly, so too much can lead to a slimy mess that smells like ammonia. All organic matter is carbon-based. It's the nitrogen content that varies from material to material, and that's what matters to composting. To simplify things, most resources separate organic matter into a brown category and a green category. The greens are nitrogen-rich, while the browns have less to very little nitrogen. Thus, you can add browns for carbon and greens for nitrogen. Greens are materials such as vegetable and fruit scraps and fresh grass clippings. Browns are materials such as dried leaves, cardboard, paper, and sawdust. In other words, fresh organic matter will contain more nitrogen than its dried counterpart. It's difficult to know the exact nitrogen content in your composting material, so to achieve the 30-to-1 carbon to nitrogen ratio, resources suggest adding 1 part green material for every 2 to 4 parts brown materials. Is this by weight? Is this by volume? Oddly, none of the sources I referenced specified which metric to use. However, I suspect it's by volume, as volume is easier to measure at home, though perhaps it doesn't matter in the long run. I started composting for one primary reason. I have house rabbits. 2 of them. And they are adorable eating and pooping machines. Every week, I'm gifted with 20 pounds of bunny poops, uneaten Timothy hay, and paper litter. The paper litter is obviously a brown. The poop, like all herbivore manure, is a green. The uneaten Timothy hay is sort of in the middle. It's dried organic matter, of course, but it was cut while it was fresh, so it contains more nitrogen than browns like dead leaves, for example. But it also lacks the moisture found in true greens. Regardless, I was tossing this material into the trash while at the same time buying bags of soil and fertilizer for my garden. I figured, why not try composting? If successful, it'll cut down on the amount of waste I add to the city's refuse system, and save money by not having to buy fertilizers and soil. But it wasn't successful. Not at first. I was pretty sure my carbon to nitrogen ratio was okay, and even if it wasn't perfect, it was close enough. My limited amount of kitchen scraps were most likely enough to boost the nitrogen levels, and besides, I really didn't want to sort through the litter box to further improve the ratio. So I decided to increase how often I turned the pile to aerate it. I had been turning it every few weeks, and I increased the frequency to roughly weekly. While I saw some improvement, it was only minor. Fortunately for my composting venture, our winter storms rolled in. In successive weeks, successive storms dropped roughly a ½ inch of rain each. A short time later, my compost pile was cooking. Softening and breaking down the paper and hay required more moisture than I originally thought it needed. And that makes sense in hindsight. The paper has the capacity for soaking up a lot of water, and the hay is dry and fibrous, even more so than lawn clippings. Further, the paper litter and hay dry out very quickly if not frequently re-wetted, at least here in my semi-arid climate. I finally had steaming, dark soil, rich in nutrients in my compost bin. And in this case, steaming is nearly literal. As the bacteria metabolize the carbon, a fair amount of heat is released. In fact, a mole of glucose, which weighs approximately 180 grams or 0.4 pounds, can release approximately 2,500 kilocalories of energy when burned. Roughly a quarter of that may be lost as heat to the environment, the compost pile being the environment in this case. Given sufficient volume and mass of the pile, the inner portion will heat up to 170 degrees F or 77 degrees C. This temperature rise occurs in 2 stages. To start, mesophilic organisms eat and metabolize until they increase the temperature to about 120 degrees F or 49 degrees C. Above this temperature, thermophilic organisms move in, taking the temperature to over 160 F or 71 degrees C. Activity then slows and the temperature reaches its steady state. At the higher thermophilic temperatures, composting occurs more rapidly, and protozoa and other dangerous pathogens are neutralized by the heat. So reaching the thermophilic stage is important to successful composting. My adventure in composting has been partly methodical trial and error, and partly throw it against the wall and see what sticks. While I might have seen success earlier in the process had I been more diligent or more scientific with the changes I implemented, I have to admit, accidentally discovering the secret recipe was a delightful experience. Thank you for listening to the STEM Sessions podcast. This episode was researched, written, and produced by me, Jarl Cody. While I strive for completeness and accuracy, I encourage you to do your own research on the topic we discussed and confirm what I've presented. Corrections and additional information are always welcome. Show notes, contact information, and details of our other activities can be found on our website, thestemsessions.com. If you received value from this episode and wish to give some back, please visit thestemsessions.com/value for value for ways to support the podcast. Finally, please remember STEM is not the exclusive tool of experts, policymakers, or talking heads. Every presenter is susceptible to unconscious and sometimes deliberate bias, so always verify what you read and what you're told. Until the next one, stay critical.